Hi everyone, welcome back to another scientific modeling episode with Blase. Here I want to take our previous discussion from the random walk, the stochastic process of a random walk where we just graphed it in a simple two-dimensional plot. And I want to take this to the next level where we actually use some three-dimensional plotting. And then I also want to add weights or probabilities of choosing certain elements in our input list. And so I'll also do that. Now, in order to do this all in a three-dimensional plot, of course, we need our random module, we need our matplotlib.pyplot module, and we're also going to need our mplot3d module. And I'm also, did I import random? I did. Did I import numpy? I did not. Let's go ahead and import numpy. Okay, great. Now that we have that, I guess I didn't run this. But okay, now that we have this, I'm going to go ahead and take our previously derived or defined function of the random walk and actually insert a couple more arguments. I'm actually going to insert an x, y, and z. I'm going to have time. We'll have the time argument, and then at the very end, I'll throw in the weights argument and show how that works. And so when we do this in 3 dimensions, really it's going to be the same process that we chose our random x for each TS value, except now we have to do it 3 different times. So I went ahead and did this code already, so I wouldn't have to do it out for you all. I changed my TS to be a ton of time increments from between 0 and the time we defined. Our x, y, and z are actually, yeah, these are placeholder lists now. And then we have a res x, y, and z, and this is actually through this code going to be the sum of all previous, or the sum of the current element plus all of the previous. And so see here we append the result of each index and element of the previous set into our resulting list x, y, and z, and then I output them as numpy arrays, res x, res y, and res z, respectively. So this gives us some sort of output list. Let's go ahead and just see the basic results of what this function would give us. If I go ahead, actually I don't want to do -2, -1. We're just going to stick with positive values for now. 0 and 1, let's do that. It's easiest to visualize. If I make time 5 and I make all of the input lists the same for x, y, and z, we get randomly choosing 0 and 1 for each step, but yet the output is the sum of all the previous. And so, or the sum of the 0 to that index. The sum of the 0 to that index of not our resulting list, but our X list. That's why it's important to have the X list as a placeholder. And so then we just append that sum of that list to the given index into our resulting list. And so our resulting list is mapping from the placeholder list. Now if I go ahead and add some more elements, you can see that now we're going to go negative randomly. Oh, let's go ahead and make that -2, so that's pretty. So we can see we're negative sometimes in some values, we're positive at other times, and you can see kind of random distribution of steps. Now if we go ahead and map this to a 3-dimensional plot, it's not that much more complicated than our matplotlib plotting. All you have to do with our imported library, or mplot3d. I like to do the ax equals plot.axis projection equals 3D. That'll turn our plot into a three-dimensional plot. I'm going to keep our input list the same, -2, -1, 0, 1, 2, and then I'm going to store our x, y, and z values as the random walk, the new definition we have, where resulting x, resulting y, and resulting z are stored as x, y, and z, and we can just plot that. See, it looks pretty random. The thing about a three-dimensional plot is that you can't really track it over time very easily. Well, when it's a line graph, if it was a surface, you'd be able to have a continuous color change based on some axis value. But when it's a line, it's really hard to do that, and so I didn't. But you can see that actually 0, this axis is here, this other 0 axis is here, and so the origin is actually up here, which is where our function, based on this 0 as well, which is actually where our function started, and you can see that it randomly went negative. Of course, if I ran it again, we'd get a different result. Our 0 is now here, mapped with there, mapped with about here. So I think that's it. That's our origin. Now, of course, you can play around with this, make this more pretty. There's a lot of limits when it comes to three-dimensional plotting with this library, but there's a lot of really cool stuff you can do with surfaces in particular, or scatters. So of course, if I did scatter, you'd see it as a scatter plot. Now, the downside for our approach for the random walk, right, is we want to be able to see where we started and where we went. So anyway. So now how do I add weights to our defined function? So we're going to go ahead and redefine our random walk again. So we have x, y, z, time, and now we're going to have this weights argument. Now what this weights argument is going to do is allow us to control the probability we choose a certain value of our input x, y, and z. So I'll go ahead and type out the code. Okay, and so what I did here is with this random choices module that we kind of used before. See, we kind of used it. What this I should say method does is it takes arguments of weights, and so the population we want to be our input lists x, y, and z. In our cases that we've used, it's just I. And then we want to weight these list elements based on weights, and so we'll just define weights as the input, or we'll just have that be an argument passed into our random walk function. And then our time, it's going to be the same as what I defined my TS linspace as, where we just have a ton of points between 0 and the time input, and that's the number of them. And so if I just passed in the number of times we pick a random thing of our population, we are actually going to end up with some sort of list, rand x, rand y, rand z, and so we're going to be able to actually completely delete this placeholder list and actually have these rand x, rand y, rand z's be our placeholder list, and then draw from them respectively in our loop. Let's make sure this runs, or I guess we'll find out if it runs when I pass some arguments into it. And so just for proof of concept with the random choices method, I'm going to show you what this outputs, where our population is 1, 2, 3. If I weight it more heavily towards the 3, you will see more 3s being chosen than 1s or 2s, where the weights, these should all add up to 1. So you can see 3s clearly show up more commonly than the 1s or the 2s in our small sample size. So that's how that works. And so if I go ahead and pass in this new weights into our random walk, If I do it really heavily towards 0, you should see more 0 elements or I guess since we're outputting the resulting list, there's going to be a lot more times where there's no step there, no step there. And then about 10% of the time we will see a step of 1, and then we'll never see a step of 2. So that's the idea of that. And you could just go, all right, well, I only want steps of 0, so I'm going to make my probability of choosing 0 1, and so that's how you get all zeros. Okay, great. I'm actually going to start on a new cell. So that's how that works. And so if we just plot this again, pretty simple with our input lists and our being the same. Of course, you could change these based on what you want your X, Y, and Z input lists that you want to draw from to change. Say if you're calculating gravity, your Z is going to be a little bit differently weighted than your X or Y. And then if you're, of course, trying to graph the pathway of some molecule that's rising, your Z is going to be different. And then, of course, the Y and the Z could be based on like wind or something like that. So over here, I just made it more probable that our drawing from our input list is going to be -1 or 1. Then I made it pretty improbable that it's going to be -2 or 2, and then 0 is 0.2 at the time. And so we can see, we can't really draw much information, but this gives us more control on our random walk. Anyway, I hope this helps do some 3D output for you. Now, what I will work on for the next video is how to change the color perhaps over time so we can track one molecule as it rises or something like that. That'll be on the next video. Anyway, thank you for watching.